All right, hi everybody. Okay, so let's get started. We got a lot to get through today, and I want to start, like I said I was going to start, by going over actually two of the problems that are assigned to you on WebAssign. And just a reminder, I got a question. There's no assignment due today. The WebAssign assignment is due next week. And so let's go to the browser. And open WebAssign. Happy Friday to you too, William. Okay, so it's scheduled due next Wednesday right now, and I think that's going to work out for us, but we'll see. I might change the due date, but that's when it's due right now. I like to see what you guys are seeing. You go into the student view. Okay, so the problems I want to talk about, I think you guys can get through this. This is asking you to do some vector addition using the tip-to-tail method, the graphical method. Okay, so you're given three vectors, A, B, and C, and asked to add them or subtract them in different combinations. Just draw a picture, tip to tail, and then connect where you start to where you end, and that's the resultant. That's your answer. All right, so I want to talk about these two problems. All right, these two problems will get at the essence of thinking about vectors as two-dimensional objects, and then there's two ways to represent them. One way is as a magnitude and a direction. In mathematics, that's often called polar coordinates. You're given a distance from the origin, that would be the magnitude, and you're given a direction, an angle, theta. The other way you could represent a two-dimensional vector is in component form, where you have an x component and a y component. All right, so let's take a look here. So here is a problem where you are given the polar coordinates to represent a vector, and in my case it's a displacement vector. It has a magnitude of 7.1 meters at an angle. Let me make this bigger. This might look a little small on your screen. There we go. I think that'll be a little better. Magnitude of 7.1 meters at a direction of 230 degrees. And the convention is, I'm never going to be able to do this. There we go. So this is the positive x-axis. The convention is angles are counterclockwise in relation to the positive x-axis. So 230 degrees is like almost all the way around the circle. All right, so let's go to my whiteboard. Okay. And the situation we have is a vector. Well, that's really kind of a vector that has magnitude r 7.1 meters at a direction of 235 degrees. So if I were drawing this, what would it look like? Let me draw coordinate axes. Here's my y-axis. There's my x-axis. So this vector r points down and to the left, something like that. How do I know? Because 230 degrees relative to the positive x-axis puts me down there in quadrant 3. Okay. So that's the setup. And so in polar coordinates, this vector, you could say, r using vector notation is 7.1 meters at 235 degrees. All right, but last time we talked about, let's change colors here. We talked about, let me redraw this vector over here. I'm going to drop the vector notation. We talked about the fact that you can resolve a two-dimensional vector into a y component and an x component, and you can do that using trigonometry. Got to know what that angle is right there. So in this case, the angle that we're interested in is the angle that the hypotenuse makes with the y component. All right, it's at the top of the triangle. All right, so I'm just redrawing that picture over here. Can you figure out what that angle is? Over here in this picture, it's that angle right there. Well, it would be theta is equal to, if we go all the way around the circle to the negative y-axis, that's 270 degrees. So that angle I labeled phi is that minus 235 degrees, which is 35 degrees. Okay, so the sign, what we could do then is use our trig functions. Yeah, you got this. Sem, do I say your name Sem or Kem? Sem? I'm horrible with names, so I apologize. Anyway, we got, so how can we find these sides of the right triangle? We use the cosine and sine function, and the sine of that angle phi, 35 degrees, equals opposite over hypotenuse, which in this case the side opposite is Rx, the x component, and the hypotenuse is R. The cosine of that angle is adjacent, which in this case is Ry over hypotenuse. So you put that all together, and you got the x component of this vector is the magnitude of the vector times the sine of that angle, phi, 35 degrees. And the y component is R cosine of phi. Okay? So at this point, you plug and chug in your calculator. Make sure your calculator is in degree mode. So phi is 35 degrees, and R is 7.10 meters for me. And when I plugged that in, I got the x component here is equal to 4.07 meters, and the y component is 5.82 meters. Okay. Holly says, you can call me Kara if that's easier. Holly, since the angle is 35 degrees, wouldn't it be the opposite side? What's that, Holly? What would be the opposite side? The cosine of, so in this case, here, turn the webcam on. So you're always defining the trig functions relative to the angle you know. So in this case, the angle we know is at the top of the triangle. So the opposite side would be the bottom of the triangle. So when we do sine, it would be opposite over hypotenuse, which in this case is the side opposite of phi is R sub x, the x component. Okay, oh, got it, great. All right, so there's one thing missing here though, and it has to do with our, well, let me go back to Chrome here. Let me put in these answers. So I got 4.07 meters for x and 5.82. And when I submit this, they're going to be wrong. Okay? Why? Why are they wrong? So this is important. Let's go back to the remote desktop. Maybe we can see the whole thing here. I know it's going to be kind of small. Colton in quadrant 3. So what does that mean in quadrant 3? So there's something about this answer that has to do with convention. The convention of direction on the Cartesian coordinate system. How's direction represented? We talked about that last time. In one dimension, what's the mathematical tool that we can use to represent direction in one dimension? Negative signs. Good. All right. So, yes, Chris. Yes, Maddie. In quadrant 3, down here in quadrant 3, x is less than 0 and y is less than 0 by definition. So since we're in quadrant 3, our vector is pointing down and to the left. That's actually in the negative direction for both of these. So, good thing WebAssign allows me to correct my mistakes. And, yay, I'm correct. And the moral of the story is, positive and negative signs, when it comes to vector quantities, positive and negative signs are the way that we communicate direction. All right. And the direction that we say is positive and the direction we say is negative, the convention is up is positive, down is negative, right is positive, left is negative. But that's a convention. You can define these things as long as you're consistent. Maybe you want to, for a problem, call up negative. You can do that as long as you're consistent. But in this case, you got to go with the convention because WebAssign is expecting the convention. All right. If you have any questions about that, put them in the comments, but we're going to move on here. And the next problem here is it deals with vectors. Well, let me go back. This might be helpful, a helpful thing to remember. So I said you could represent this vector. One way you could represent this vector is in polar coordinates, like so. And another way you could represent this vector is using x and y components. So I could do, down here, r equals the x component times its unit vector, I hat, plus the y component, j hat. And then we got to include units. It's a displacement vector, so it has units of meters. So what would that look like? It would look like this. R equals minus 4.07 I hat plus minus 5.82 j hat meters. Okay? So you can represent this vector in unit vector notation with its x and y components. All right? So there's two different ways you can do that. So this next problem deals with this way of representing a vector. All right? So you got this displacement vector d, which is 4 I hat minus 7 j hat. Find the displacement vector r so that d plus r equals this other thing, 6 minus 6 d j hat. Express your answer in vector form. All right. So let me record this information on my, I'm trying to record this on my whiteboard here. All right, the situation we have is vector D equals 4 I hat minus 7 j hat meters. And then the other information we have is D plus some other vector R equals minus 6 d j hat. And what you're asked to find is, well then what is R? And that's ultimately what you're looking for. Alright, so there's a really important lesson here when it comes to dealing with vector quantities. And it's, well, one lesson is that you can rearrange expressions like this algebraically. So if D plus R equals this thing minus 6d j hat, then R is going to equal minus 6d j hat minus D. Just rearrange that to get that new way of representing it. All right, so my question for you here is, when you look at this problem, let's look at it. This D and this R are vectors. You can tell because they're bold and they have the arrow above them. What the heck is this D? It's something different. What is that? What do you think that is? Tell me. Tell me in the comments. What the heck is that thing? Right there. That D. Anybody care to guess? Nobody? Nobody feeling confident on this Friday morning? All right, I'll tell you. So, this D right here, it's not bold and it doesn't have the arrow on top of it in the problem. What that's telling you is that D equals the magnitude of the vector D. Another way you can write that is with this kind of symbol, with these vertical lines around the D. So that's what the D is without the arrow on top of it. It's the magnitude. So if we think about, there's sort of a little aside here. Let's do it in green. If we have an x and a y axis, D has a positive x component and a negative y component. So D points down and to the right, something like that. So this is 4 meters this way and 7 meters down. So the magnitude of D right here is the length of this arrow. What is it? It's the Pythagorean theorem. So if you solve this for D, you get, well, it's not a nice number, it's 8.062 meters. So D has an x and a y component. Its magnitude you can figure out, you know, I drew a picture here, but you can figure out using the Pythagorean theorem. All right. Okay. So that's what this is right here. This is 8.062. It's the magnitude of D. All right. So now we can solve this problem, and it's not that bad. Okay. What I'm saying here is we're trying to find R. Right, picking up where we were up here, it's going to equal minus 6 times the magnitude of D, which we just found. It's 8.062 meters, j hat minus, you write it down here, D itself vector d, which is 4I hat minus 7j hat meters. Okay, sorry, my pen is acting weird today. I think it's broken. See, this is what I'm writing with on my tablet, on my Surface, and you probably can't see that, but the tip is getting wonky. That sucks because these pens are like $100. All right, so how do I solve this? Well, so here's the magic of vectors in vector component, or in x and y component form. The magic is that you can think of it as two problems. There's a problem in x and a problem in y. And if you're adding vectors, you add all the x components and you add all the y components separately. And then at the end, you could put them back together if you want. And so this is going to be a recurring theme this whole semester. When you have vector quantities like forces, velocities, displacements, break those two-dimensional vectors into x and y components, and then usually what you have is an x problem and a y problem, and you can do them independently. And then there's something that connects the two. We'll get to that eventually, but a little foreshadowing. All right, so what I'm saying here is let's group the x components together. So this first term doesn't have an I hat component. So the I hat component, the x component of the total, is just going to be minus 4. And then for the j hat component, we're going to have to add the 6 times 8.62 and minus minus, so that would be plus 7 j hat. And we'll tack our units on here. So those two, it's kind of like now in this case, algebraically the I hat and the j hat are like variables, so you can group like terms. That's what I'm doing here. So when I multiply 6 by 8.062, I get a negative large number, and then I add 7. And when I put this all together, the final answer I get is minus 4 I hat plus negative 41.4 j hat meters. Okay, so that's the answer I get. Let's go to Chrome and let's see how we enter this. So this is an example of one of those. Remember I said that some of these problems on WebAssign you're going to enter your answer symbolically. So this is an example of one of those problems. So watch what happens when I click on this box. This pop-up window comes up, and so one of the things you can do is you can select unit vectors, I, J, K. All right, so what I'm going to type here is minus 4, go to my vector window, I hat, and then plus negative 41, so that's the same as minus 41.4 j hat. So these, you might say, well, where the heck are the hats? It's just I and J. Well, they're bold. You may not be able to tell that. You can see that over here. There's different ways to communicate whether something's a vector quantity or not. You can, you know, like here we have the arrows over top of the D and the R. Another way to communicate that something is a vector quantity is to just make it bold, and textbooks do that all the time. All right, so let's submit this answer. Good, we got it. All right. So, you know, your problems are different numbers, but it's the same idea, and but there's really important lessons here. You know, these are just the first problem has you think about vectors in like this polar coordinate fashion where you have a magnitude and a direction. Use your trigonometry to decompose that into an x and a y component, and then you can represent it, that vector, via its x and y components using I hat and j hat. The other thing that's really important is this idea that once you resolve vectors into components, the x components can add together, the y components can add together. So it becomes two separate problems. There's a problem in x and a problem in y, and that's a theme that's going to be repeated a lot this semester as you do problem solving. All right, let's see what's next. Okay, so what I want to do now is I want to return, we've been talking about mathematics of vectors, so now I want to return and actually talk about some physics. All right. And I think I'll start a new whiteboard here. Okay. So the topic of the week is, sorry, I'm really kind of struggling here. There we go. Motion in one dimension. Okay, motion in one dimension. And we talked about, here's a little dude running, and he's running in this direction, and starts out at some position x naught, and then sometime in the future he's at some other position x. So you can think of x as a function of time, where time is how long it took him to travel this distance. All right, so one thing we can do is we can define a displacement vector. We'll call that delta x is final minus initial. Okay, so for the, I think what I'll do is, I'm going to write a lot of equations down in the next 20 minutes, and I don't want to, I don't want you to forget that a lot of these quantities are vector quantities. They have magnitude and direction, but I'm not going to put the little arrow over all of the symbols, just for simplicity. Okay. Okay. So we already said, well, if you know how far something travels in a given interval of time, you can calculate, and so here, this is average velocity. It's equal to that displacement divided by that interval of time. Okay? Sometimes you might see it like this. You might see, well, average velocity equals delta x over delta t. But, delta x, it makes a lot of sense. It's x minus x naught. It's delta t versus just using a t. There's not much difference there, and the reason is because oftentimes when we're thinking about time, we always have a stopwatch that starts from 0. So if you have like t minus t naught, your initial time is usually 0. So you don't really gain much by writing delta t versus just t. All right, again, these are actually, this delta x is actually a vector quantity, but I'm not going to put the little arrow on top of it. And one thing, you'll learn in calculus when you talk about limits is you can think about, what happens to this quantity in the limit where the interval of time goes to 0. And what you get is you get an average velocity over an infinitesimally small interval of time, and that is called instantaneous velocity. I really need to get a new pen. It's like trying to write with a wet noodle. Okay, and you guys who are in calculus now or have taken it before, what you'll see here is another way of thinking about this is as a derivative. So the limit as delta t goes to 0 of this thing over here is also the derivative of x with respect to time. Okay, so these are equivalent ways of thinking about velocity in the limit. Let me say that this way. So when we define velocity, what we're really defining is average velocity, because in practice, velocities involve changes, a change in position, a displacement, and a change in time, t. And so in the real world, in order to estimate a velocity, you'd have to measure those changes. But we can conceptualize and use mathematics, formalize this idea that you could think about what happens as that interval goes to 0, gets infinitesimally small. And what happens is now you're looking at one moment in time, the instantaneous velocity. All right. All right. So I'm sorry, that keeps moving on you. Okay, so one thing that is true is you can easily imagine a situation like this, where you have this runner, he's really, hold on, I can do better than that. Got this runner, there you go, and he starts out with the stopwatch at 0 seconds. And I really apologize for this. I got to do something about this pen. Maybe if I just slow down a little. And then sometime later, 1 second later, so t equals 1 second, this is where he is. And then after 2 seconds, this is where he is. And after 3 seconds, this is where he is. So what we have here is uniform intervals of time, but delta x during each interval is getting bigger and bigger and bigger. So if you used this knowledge to calculate average velocity, what you see is the average velocity is getting bigger and bigger and bigger. So you have a situation where velocity itself is changing. Velocity is a change in position with respect to time, change in displacement with respect to time. Here we have a situation where the velocity itself is changing with respect to time. And that is acceleration. All right? So what I'm doing here is I'm showing you an example of a guy running and accelerating. And acceleration is defined, average acceleration is a change in velocity over a change in time. And just like before with velocity, we can say, well, what happens as that interval of time gets smaller and smaller? In that limit, you have instantaneous acceleration. Okay, and just like before with velocity, alternate way of thinking about this is the limit as that interval delta t goes to 0 is the same as the derivative of v with respect to t. Okay. This reminds me, I posted under the lessons on Sakai a summary of things that you should be doing independently And one of those items on that list is a link to a video, which is an introduction to derivatives. And if you are in calculus right now, you should definitely watch that. That will help you a great deal. The fact that you're taking calculus concurrently with this course means that you haven't learned the language of calculus yet. But I'm going to use it from time to time. So you watch that video and it'll probably help you in calculus. It'll make you, it'll increase your calculus grade, okay? And if you haven't done calculus in a while, it's worth watching, okay? So, you know, check that out. It's under lessons, week 1. There's a link to a video I made a couple years ago. The production value, not very good, but it gets the job done, I think. All right. So back to our task here at hand. So what I've done is I've laid down for you 2 physics first principles. Let's call them that. And the one is there's a definition of velocity, and the other one is there's a definition of acceleration. Velocity is change in displacement with respect to time. Acceleration is a change in velocity with respect to time. So both of these things, velocity and acceleration, are vector quantities. And that shouldn't be hard for you to internalize, because remember, vectors have magnitude and direction. And you know, obviously velocities have direction. You know, I could go left, right, up, down. There's direction associated with it. Acceleration, that might be a little bit more nebulous to you guys. How could acceleration have a direction? And my answer to that is what we mean by direction isn't necessarily the same thing as what we think of as direction on a map. All right? Maybe another way to think of it is flavor. There's 2 flavors of acceleration. One flavor is something speeding up, and the other is something slowing down. Sometimes we call that deceleration. And so we'll explore that idea in lab next week, via my computational lab that I have for you next week. But you'll explore it in the textbook as well. All right. So I got 12 minutes. We can do this. What I'm going to do is in this course, let's go over here and zoom in a little bit. All right. So in this course, we're going to limit ourselves analytically, algebraically, to the situation where acceleration is constant. Okay. And acceleration being constant could include 0, acceleration equal to 0, because 0 is a constant. All right, but we're going to restrict ourselves to situations like that. And in the case where acceleration is constant, the average acceleration is equal to the instantaneous acceleration. It's like, you know, if you have something that's not changing, its average over an interval of time is whatever it is, because it's not changing. All right, that's what I'm saying here. But the reason we're doing that is because then we can say instantaneous velocity is equal to change in velocity over time, or final minus initial divided by t. Let me write that again. Final minus initial divided by t. All right. Then the other pieces that we have, these other first principles, are this idea that average velocity equals change in x, delta x over t. And then let me write down one more thing. And so this is true because acceleration is constant. So another way, and this is the, you know, this is, I think that if you think about it, you're like, well, this makes complete sense. But if you have a quantity and you want to know what its average is over an interval of time, and that quantity can change, because acceleration, it could be accelerating or decelerating, but the rate of change is constant. Um, Another way you can think about the average is, well, what was it when you started? What was it when you ended? Add those two things together and divide by 2, and that gives you the average. What is that? That's just the arithmetic mean. If you want to know the average of two numbers, beginning and end, add them together and divide by 2. So it turns out that this is a pretty useful thing for us mathematically here. So what I'm saying is another way you can write the average velocity is just what it was when you started, v naught, plus what it was when you ended, v, divided by 2. And so if we call these our first principles of of a physics man, this is ridiculous. I wonder where I can get a new Microsoft Surface Pen. I can't see that. It's like a little limp noodle there on the end. The first principles of this area of physics is called kinematics. It's concerned with describing motion. So we can call these the first principles of kinematics. And then what we can do is, and this is algebra. We can take these 3 equations and combine them in a lot of different ways to come up with new equations. And you might say, why would you do that? And the reason you would do that is because these algebraic equations are only useful as tools for solving for unknowns if there's only one unknown in the equation. And like maybe there's a time where you don't know what the acceleration is, but you know how fast you're going at 2 moments in time, and you know how far you traveled during that interval of time. So this next stuff that I'm talking about, I'm not actually going to go through the derivations of all these equations because they're in your textbook. I'll show you where they are, and then I'll write out the final solutions. But these equations, they're often referred to as the kinematic equations of motion, and they are your toolbox for doing problems involving describing how things move when those things have a velocity and they may or may not be accelerating. All right. So I think I'll just rewrite these. So another way you could write the first equation, it's oftentimes written like this. Instead, well, that's weird. What have I done? I don't want that ruler. Go away. Okay. Instead of writing a equals v minus v naught over t, you can rearrange it. V equals v naught plus a times t. So maybe those are the 3 most useful ways of thinking about these equations. All right, so let's go to the textbook. Let's see, there's problems. Here we go, where you're using. Nope, I want to go to the next section. Yeah, 3.4. Okay, make this a little bigger so you can see it. Here we go. So you see equations in here, like this is, and make it even bigger. You know, here's one of our first principles of motion. Average velocity is a change in position over time. And here they're saying, well, you could rearrange it like this. Where you are is where you were plus how fast you were going on average times time. Here's another way of writing average velocity, and then they define acceleration and say, well, you could write it like this. How fast you're going is how fast you were going plus your rate of acceleration times time. And there's examples in here, so it's a good read. Okay, so then what it's saying is, well, let's take this equation and let's rearrange it by doing some algebra, and then let's make a substitution for average velocity, and then let's solve, simplify. You can derive this equation right here. And this equation would be useful in a situation where you don't know how fast you're going, v, at the end of some interval of time, but you know your rate of acceleration, you know where you are, where you started, x and x naught, and you know how fast you were going when you started. All right. And so let's add that to our toolbox. All right. And it's, I don't know if you're into this sort of thing. I find this somewhat enjoyable to do algebra like this. You could challenge yourself to try to follow along with these derivations in the textbooks and do it yourself, and combining these equations to get these new forms. But combining these three equations over here, one of the things you get is this new fourth equation, x equals x naught plus v naught t, it's weird, why is that there, plus 1/2 a t squared, okay? All right, well, what if you don't know time? Well, let's use these same formulas and rearrange things. So we'll solve the acceleration definition for time, and then we'll plug that into the definition of velocity for time right here, and we'll substitute away the average velocity using this other expression for average velocity and rearrange, and you get this expression, v squared equals v naught squared plus 2a times x minus x naught, the quantity x minus x naught. So we get a fifth equation to add to our kinematics toolbox. All right, so let's write that down. V squared equals v naught squared plus 2a x minus x naught. Okay, so our kinematic equations of motion, our kinematic equations of motion are these guys. All right, those equations, and so it's important for you guys to understand that these two equations over here are not some sort of unique thing. What they are just algebraic manipulations, algebraic combinations and simplifications of these three equations over here. All right. So these guys are not unique. These guys are the foundation of these guys. Okay, but sometimes these are useful, so it's worth deriving. All right, I know I got like 10 seconds here, so let me end by saying, here they are in your textbook. Zoom out a little bit. There's a gray box that summarizes these kinematic equations of motion. All right, they're right there. And you should, they're also on, this is in section 3.4. They're also on the equation sheet that's on Sakai. And those are, in that form, that's what you'll get on the exams. And so now problem solving, in the last part of the homework assignment, the problem solving takes the form of this. It's a word problem. You're given some things that you know, and you're asked to find something that you don't know. And a good way to approach it is, well, let me write down my knowns and let's see if any of these equations in the toolbox connect what I know with what I don't know. In other words, the only thing in that equation that I don't know is the thing I'm looking for. And that's the strategy you go through. So on Monday, I'll pick one of these problems and we'll do it together, all right? But you should be able to do them now. And it's worth struggling a little bit with them to, you really learn when you struggle a little bit. Anyway, that's it for today. And next Friday, I hope that we can see each other in person for the first time, and at least some of you. see you in person, and I'm working on that and figuring out how to handle that. But have a good weekend. All right, and until then, I'll see you later.